Until now, I have given you a set of lectures on finite dimensional linear vector spaces, emphasizing concepts like operators, operator algebra, states, the role of matrices, matrix representation of operators, and so on. The importance of Hermitian operators, the importance of unitary operators. I have demonstrated many of these concepts using the 2-level atom and the 3-level atom as examples. We have also looked at the spin half system or the spin doublet, the spin triplet, and so on. The concepts that I have been taught till now would perhaps become clearer if we did a set of problems at this point, a set of exercises or tutorials, and brought out the importance of some of these concepts better by working out certain specific problems and certain aspects of finite dimensional linear vector spaces using specific examples. So, we would just have exercises in finite dimensional linear vector spaces. So, today we will work out some exercises. The first one would be a recapitulation of what has already been done during the lectures. I told you that the eigenvalues of a Hermitian matrix are real, and eigenvectors corresponding to distinct eigenvalues of a Hermitian matrix are mutually orthogonal. Let me quickly recapitulate the proof of that statement. Let A be a Hermitian matrix. Of course, in order to show that this is an operator which is represented by a matrix, we could put a hat on top. I would, for the sake of simplicity, dispense off with the hat, and we will remember at the back of our mind that A is a matrix and a Hermitian matrix. The dagger would represent, transpose, interchange the rows and the columns and take the complex conjugate of every element. Suppose psi were an eigenstate of A and the corresponding eigenvalue is little a, then surely this is true. If I take the dagger, since A dagger is the same as A, I have this. The aim is to show that A is equal to A star, and that can be simply done as follows. Start with equation 1 and do this. Let us imagine that psi is normalized to 1. Then the expectation value of A in the state psi is simply A. But I could have started with equation 2 and I could have done this. That is the same as A star psi psi, and this object is 1. From equations 3 and 4, it is clear that psi A psi is equal to A and also equal to A star, which implies that A is equal to A star. So, eigenvalues of Hermitian matrices are real. Let me also quickly recapitulate how the eigenvectors are mutually orthogonal to each other if they correspond to different distinct eigenvalues of A. So, for that purpose, let us take 2 eigenvectors satisfying this eigenvalue equation. A1 is not equal to A2, that is given. They are distinct eigenvalues. Also A1 and A2 are real because A is Hermitian. Then from equation 1, I get this. I also have, so this object is there, I also have the bra of this. psi 1 A is equal to A 1 psi 1. Now, I could well do psi 1 A psi 2. A psi 2 is A 2 psi 2. And A psi 1 is A 1 psi 1. So, I have these two equations. On the one hand, I worked with A on psi 2, pulled out an A 2, and I had an inner product of psi 1 with psi 2. On the other hand, I know that because A is Hermitian, A dagger is the same as A, and here I have psi 1 A should have normally been A 1 star bra psi 1, but because A 1 is real, I have just written down A 1 there, and therefore I have A 1 psi 1 psi 2. This clearly means that A 2 inner product of psi 1 with psi 2 should be the same as A 1 inner product of psi 1 with psi 2, but A 1 and A 2 are not equal to each other. That is given to us, implies psi 1 psi 2 is 0. Therefore, eigenvectors corresponding to distinct eigenvalues of a Hermitian matrix are mutually orthogonal. So, this is a quick recapitulation of what was already done during one of the lectures. I want to work more with Hermitian matrices. The next thing I want to show is the following. We are working with finite dimensional linear vector spaces, and I want to show that the eigenvectors of a Hermitian matrix form a complete set of states. In other words, they can be used as a basis set in terms of which all other states in the linear vector space can be expanded. So, basically I need to show that the eigenvectors of a Hermitian matrix span the entire linear vector space. They form a complete set. To prove this, I do the following. Let us imagine that the eigenvectors of the Hermitian matrix A span a subspace M of the linear vector space. In other words, we are now saying that let us imagine that the eigenvectors do not span the entire linear vector space. All states in the linear vector space cannot be expanded as a superposition of the eigenvectors of the Hermitian matrix. The idea is to show that there is a contradiction if we imagine so. So, there is a subspace M bar of the LVS which is not spanned by the eigenvectors of A. the total linear vector space is composed of M and M bar. Now consider the projection operator. Let E be the projection operator onto the space subspace M. Let me quickly recapitulate what is meant by a projection operator. We have seen projection operators both in the context of the 2-level system and the 3-level atom. So if you recall, in the case of the 2-level atom, the projection operator 1 1 for instance would act on any arbitrary state A times ket 1 plus B times ket 0 for instance. So these are the 2 levels 0 and 1. If you wish, you can call this G and you can call this E. So by 1 1 in this notation I mean E E. That projection operator certainly gives you A times ket 1. So this is the projection operator onto the subspace of the linear vector space, which is spanned by the basis state 1. Similarly 0 0 acting on any arbitrary state gives me B 0, and this is therefore the projection operator onto the subspace spanned by ket 0. It is evident that 1 1 plus 0 0 is the identity. In the language of ket E and ket G, we showed that E E plus G G was the identity. So here we have a situation where we do not have just 2 basis states, but in general we have many states spanning the space. Now let E be the projection operator onto the subspace M. Then surely identity minus E is the projection operator onto the subspace M bar. That is like saying that if E E is the projection operator onto the space spanned by ket E, identity minus E E is the projection operator onto the space spanned by ket G. In the 2-level atom problem, that would be the corresponding statement. Now consider the operator A times identity minus E. Since identity minus E is the projection operator which acts on any state in the linear vector space and projects it onto the subspace M bar, A M bar is an operator which surely has at least one eigenvector with a corresponding eigenvalue, and let us imagine that that eigenvector is phi with corresponding eigenvalue A. This is a matrix, an operator with a matrix representation. I would therefore expect it to have, it is a Hermitian matrix, I would expect it to have one eigenvalue at least with a corresponding eigenvector. But this object, therefore phi is an eigenvector corresponding to this operator. Now consider A phi. A phi can well be written as A E phi plus A times identity minus E phi. But phi is a vector in M bar, therefore E phi is 0 because E is the projection operator onto the state M. So there is nothing to project into the subspace M, and therefore A phi is the same as A times identity minus E phi, which is A phi. In other words, what we have seen is that a state which belongs to M bar is an eigenstate of A with eigenvalue A. But all eigenstates of A we imagined would span only the subspace M. Therefore, there is a contradiction. Here we have a state phi which initially we said belonged to the subspace M bar, but we have now seen that it is one of the eigenvectors of A, and therefore, the eigenvectors of A span the complete linear vector space, the full linear vector space. In other words, they are a basis set for the entire linear vector space and not for a subspace. This is an important point because we have just established that the eigenvectors of a Hermitian operator span the entire linear vector space. In other words, they act as the basis set in terms of which every state in the linear vector space can be expanded. Now we move on to the next problem, which is a very important problem, and that is to show that if two Hermitian operators commute, you are guaranteed to find a complete set of common eigenstates of these two Hermitian operators. So, that is the next problem. And this is something which should be proved systematically. So, the statement is this: if two Hermitian operators could well be matrices A and B commute with each other that is commutator of A with B is equal to 0, then there exists a complete set of common eigenstates of A and B. You will recall that this too has been established in the context of the spin system, where we had two Hermitian operators S squared and Sz which commuted with each other. So, we had S squared Sz commutator equal to 0, and we found a complete set of common eigenstates labeled by the two quantum numbers S and M, and we certainly demonstrated in the case of the two level atom that this could be written as S into S plus 1 h cross squared S comma M, and Sz acting on Sm is M h cross Sm. So, this is a complete set of common eigenstates where S takes a certain value and M takes values from minus S to plus S in steps of 1. While we did not establish that M indeed takes values in general between minus S and plus S, we certainly demonstrated that that is what happened in the case of the two level atom, where we had two states half half and half minus half. So, that for S is equal to half, M took values plus half and minus half, that is plus S to minus S in steps of 1. We now have to establish this statement that in general, if two Hermitian operators A and B commute, then you are guaranteed that there exists a complete set of common eigenstates of A and B. So, that if you measure A and B in the system simultaneously, the system will collapse to one of this complete set of common eigenstates after the measurement. We prove this as follows. Let psi be an eigenstate of A with eigenvalue alpha. Then B A psi is alpha B psi, but B A psi is also equal to A B psi, because A and B commute with each other. Therefore, A B psi is alpha B psi, where alpha is the eigenvalue of A corresponding to the eigenvector psi. We have then shown that B psi, this is another state which I will call chi, because it is an operator acting on a state, it gives me another state. We have established therefore that B psi is also an eigenstate of A with eigenvalue alpha. This means the following. There are many cases here. The first case is alpha is non-degenerate. Non-degenerate eigenvalue means that there is exactly one eigenvector corresponding to that eigenvalue. So, the first case is alpha non-degenerate. There is no more than one eigenvector of A corresponding to that eigenvalue alpha. Degenerate would mean that there is more than one eigenvector, maybe 2, maybe 3, maybe many more. All these eigenvectors are eigenvectors of A corresponding to the same eigenvalue alpha. So, there are cases to be considered. The first case is alpha is non-degenerate, which means that if you have A psi is alpha psi and A chi is also alpha chi, and alpha is non-degenerate, chi is clearly linearly dependent on psi. In other words, some A chi plus B psi equal to 0, A B not equal to 0. Therefore, chi is minus B by A psi, or chi is equal to some beta psi. That is the only way by which this could have happened. Clearly, this means writing chi in terms of B psi is equal to beta psi. What is it that we have established? If psi is an eigenvector of the Hermitian operator A, we are only concerned with Hermitian operators. If psi is an eigenvector of the Hermitian operator A with eigenvalue alpha, and alpha is non-degenerate, and if B is a Hermitian operator which commutes with A, psi is also an eigenvector of B, in general with a different eigenvalue beta. We have already shown earlier that the eigenvectors of A form a complete set which spans the entire relevant linear vector space. Since the set of psi's form a complete set of eigenvectors of A, and since these are also eigenvectors of B, it is clear that in this case A and B have a complete set of common eigenstates. So, the first part was proved earlier, that the eigenvectors of a Hermitian operator in a finite dimensional linear vector space form a complete set. In the event that alpha is non-degenerate, it is clear that this complete set of eigenvectors of A is also the complete set of eigenvectors of B, and therefore, there is a complete set of common eigenstates. I have worked with just psi. You can look at the complete set of eigenvectors of A and the argument would go through as such. The more non-trivial case is where alpha is degenerate. So, let us look at the second case, alpha degenerate. Let us say G-fold degeneracy. What does that mean? There are a set of G eigenvectors of A, all of them corresponding to eigenvalue alpha. In other words, A psi I is alpha psi I takes values 1, 2 all the way to G. So, that is a G-fold degeneracy. The eigenvalue is G-fold degenerate. To illustrate whatever follows, we will look at the simplest case where G is 2. So, we will have two-fold degeneracy. Whatever I say for G is equal to 2 can be easily extended to n-fold degeneracy. So, let us look at the case when G is 2. Before that, we recall that we have already established if alpha is non-degenerate and A B equal to 0, A and B have a complete set of common eigenstates. So, now alpha is, we are looking at the second case of degeneracy, and there we look at the simple example G is equal to 2. In other words, there are two eigenstates psi 1 and psi 2 with eigenvalue alpha. Consider a linear combination psi written this way, where C1 and C2 are for the moment arbitrary constants, no conditions on them. Then A psi is C1 A psi 1 plus C2 A psi 2. That is the same as alpha C1 psi 1, because A psi 1 is alpha psi 1, and similarly A psi 2 is alpha psi 2, therefore, I have C2 psi 2, which is alpha psi. So, any arbitrary linear superposition of psi 1 and psi 2 is also an eigenstate of A with the same eigenvalue alpha. Now, let us look at B. We wish to know if it is possible to find some set of values for C1 and C2 such that B psi is beta psi. In other words, would all linear superpositions of psi 1 and psi 2 given in general by C1 psi 1 plus C2 psi 2, would all such linear superpositions be also eigenstates of B, of course in general with a different eigenvalue beta, or are there conditions on C1 and C2? Is it at all possible to find a complete set of common eigenstates of A and B if alpha is degenerate? That is the problem that is being addressed. So, this is the same as saying expanding psi in terms of psi 1 and psi 2 we have this. Now, let us go ahead and do the following operation. Psi 1 be C1 psi 1 plus C2 psi 2 that is clearly beta psi 1 C1 psi 1 plus C2 psi 2. C1 is a number which can be pulled out, psi 1 b psi 1, C2 is a number, so the second term gives me psi 1 b psi 2, and that is what I have in the left hand side. That is beta C1 psi 1 psi 1 plus beta C2 psi 1 psi 2. I have already assumed that psi 1 and psi 2 are orthogonal to each other, and therefore I have a shorthand notation B11 for this, B12 for that. This is normalized to 1. So I have C1 B11 plus C2 B12 is beta C1. In other words, C1 times B11 minus beta plus C2 times B12 equals 0. Let me call that equation 1. Similarly, I can do the same operation, except that I can use psi 2 there instead of psi 1. And then what do I get? Psi 2 b C1 psi 1 plus C2 psi 2. I am using psi 2, okay, is equal to beta psi 2 C1 psi 1 plus C2 psi 2. Once more, the first term gives me C1 B21, where B21 is simply psi 2 b psi 1 in my notation, plus C2 B22, and B22 is psi 2 b psi 2. This object is clearly equal to C1 beta psi 2 psi 1, but that term is 0, plus C2 beta psi 2 psi 2, but that term is 1. Therefore, I have C1 B21 plus C2 B22 minus beta is equal to 0, and I call this equation 2. So, I have these two equations, C1 B11 minus beta plus C2 B12 is 0, and remember that B11 and B12 are simply numbers. Similarly, C1 B21 plus C2 B22 minus beta is equal to 0. Now, clearly, if indeed it is possible to have this superposition to be an eigenstate of B with some eigenvalue beta, the determinant of the coefficients given this way should be 0. This determinant should be 0 because I have two homogeneous equations in C1 and C2, and in order to have a solution I need to have this determinant equal to 0. That is going to place conditions on beta, and the beta is the eigenvalue corresponding to the eigenvector of B, and therefore that should tell me what the values of beta are. In other words, I have reduced this to finding out the possible values of beta. So, this determinant when expanded gives me B11 minus beta times B22 minus beta minus, recall that B12 and B21 are complex conjugates of each other, because B12 is psi 1 b psi 2, which is a number, and B21 is psi 2 b psi 1, which is the complex conjugate of that. Therefore, I can write this as b11 minus beta times b22 minus beta minus modulus of b12 the whole squared is equal to 0. This is the equation I have to solve, and beta will, it is a quadratic in beta, so I will have two roots, beta squared plus beta times minus b11 minus b22 plus b11 b22 minus modulus of b12 the whole square. So, beta 1 is this, that is beta 1, and beta 2 again is the solution minus root of the same quantity b11 plus b22 the whole square minus 4 b11 b22 minus modulus of b12 the whole square by 2. I now have various cases to discuss. Recall that alpha was twofold degenerate, and we had A psi is alpha psi, where psi was C1 psi 1 plus C2 psi 2. Now, I have a situation where I have two roots beta 1 and beta 2, and I demand that B psi is beta psi, that psi is a common eigenstate of A and B. Is it possible to have these two roots equal? Yes, it is possible. Beta 1 equals beta 2 if this quantity within the square root is 0. So, if b11 plus b22 the whole squared minus 4 b11 b22 plus 4 mod b12 whole squared is 0. So, certainly if this vanishes, then beta 1 is b11 plus b22 by 2, and so is beta 2. So, let us expand this, that is b11 squared plus b22 squared plus 2 b11 b22 minus 4 b11 b22 plus 4 mod b12 squared equal to 0. Now, that is like saying b11 minus b22 the whole squared, because this gives me a minus 2 b11 b22 between these two terms, plus 4 mod b12 the whole squared equals 0. If this were true, then beta 1 is equal to beta 2, no conditions on C1 and C2. Since both of them are positive quantities, this implies that b11 is equal to b22 and b12 is equal to 0. I could write modulus of b12 is equal to 0. Then beta 1 is equal to beta 2. From here, this is just b11. This term drops out, and so beta 1 is twice b11 by 2. Beta 2 is also twice b11 by 2. So, that is b11, but that is the same as b22. Remember, mod b12 is equal to 0. And then we have shown, therefore, that b psi, this psi was a linear superposition C1 psi 1 plus C2 psi 2 is equal to beta psi with beta equal to B11 which is the same as B22. It clearly follows that psi 1 is an eigenstate of B with eigenvalue beta and psi 2 is an eigenstate of B with eigenvalue beta. I therefore have C1 psi 1 plus C2 psi 2 is B11 C1 psi 1 plus C2 psi 2. This is true for any C1 and C2. Therefore, I have B psi 1 is B11 psi 1, B psi 2 is B11 psi 2. Remember the beta was B11 and any linear combination B psi is equal to B11 psi. In other words, we have shown that with no conditions on C1 and C2, in other words, any superposition of psi 1 and psi 2 would also be an eigenstate of B. The eigenvalue is degenerate, again twofold degeneracy, because there are two states psi 1 and psi 2 corresponding to the eigenvalue beta, which turns out to be B11 in this case. So, what is it that we have established? If alpha is twofold degenerate, that is A psi 1 is alpha psi 1 and A psi 2 is alpha psi 2, it is possible that B psi 1 is beta psi 1 and B psi 2 is beta psi 2. The degeneracy is not lifted and the set of eigenstates of A are also eigenstates of B. We have found that set. So, we have a complete set of common eigenstates of A and B. The degeneracy has not been lifted. On the other hand, it is possible that the degeneracy gets lifted, and that is the case that we will consider now. So, returning to the solutions beta 1 and beta 2, let me recall that we have considered the case where this object within the square root is 0 and therefore beta 1 was equal to beta 2, but in general beta 1 need not be equal to beta 2. So, that is the case that we will consider now. What does that mean? That means that that square root is not 0. So, B11 plus B22 the whole squared is not equal to 4 times B1 B2 B11 B22 minus modulus of B12 the whole squared. So, we are looking at a situation like this. As you can see, this simplified, if this were equal, it simplified to B11 minus B22 the whole squared plus 4 modulus of B12 the whole squared equal to 0. So, we are essentially saying B11 minus B22 the whole squared plus 4 modulus of B12 the whole squared is not equal to 0. In general, beta 1 would not be equal to beta 2 if any of these quantities is non-vanishing. If B11 not equal to B22 or mod B12 not equal to 0. So, we can consider the case, the first case, B11 not equal to B22, and for simplicity mod B12 equal to 0, or B11 equal to B22, but mod B12 not equal to 0. In either case, beta 1 is not equal to beta 2, and we have two different roots corresponding to the quadratic in beta. So, let us look at this situation. let us look at the first situation, B11 not equal to B22, B12 equal to 0. So, that is the situation that I intend considering now. So, what is beta 1? Beta 1 is B11 plus B22 by 2 plus square root of B11 out there minus B22 the whole squared. Divided by 2. So, this object is simply B11 by 2 plus B22 by 2 plus B11 by 2 minus B22 by 2, which is just B11. Similarly, beta 2 is the other object B11 plus B22 by 2 minus square root of B11 minus B22 the whole squared, the whole by 2, which is the same as B22. So, I have two roots, beta 1 is equal to B11 and beta 2 is equal to B22. What does that mean? It means the following, that there are two eigenvalues C1 psi 1 plus C2 psi 2 is equal to B11 C1 psi 1 plus C2 psi 2. So, let me consider this. Similarly, I have another eigenvalue B22 and I have some superposition. So, let me consider this and let me look at C1 equals 1 and fix C2. So, if I took C1 equals 1 and if I work with psi 1 on this side as before, B11 is a number, so I can pull that out. This gives me C1 B11 plus C2 B12, but that object we said was 0, is equal to C1 B11, which is just a consistency condition. I have put C1 equals 1. If I now do psi 2 B times C1 psi 1 plus C2 psi 2, that object is B11 psi 2 times C1 psi 1 C2 psi 2. By this I mean the inner product. The first term gives me C1 B21, but that is 0. If B12 is 0, B21 is 0, plus C2 B22. The first term is 0 because psi 2 psi 1 inner product is 0, but the second term survives and that is C2 B11. If C2 B22 should be equal to C2 B11 and B11 is not equal to B22, it implies that C2 is equal to 0. In other words, I have established the following. I have established that B psi 1, because C1 is equal to 1 and C2 is equal to 0, I have established that B psi 1 is equal to B11 psi 1. Similarly, I can start with B times C1 psi 1 plus C2 psi 2 equals B22 C1 psi 1 plus C2 psi 2. Proceeding on the same lines as before, I can now show that in this case, if C2 is 1 and C1 is 0, it follows then that B psi 2 is B22 psi 2. What is it that I have established? I have looked at a very specific case where B11 is not equal to B22 and B12 is equal to 0, and I have shown that there are two eigenvectors psi 1 and psi 2 which are eigenvectors of B, except that the degeneracy is now lifted. One of them comes with eigenvalue B11 and the other comes with eigenvalue B22. So this situation corresponds to alpha is twofold degenerate, A psi 1 is alpha psi 1, A psi 2 is alpha psi 2. However, B psi 1 is B11 psi 1 and B psi 2 is B22 psi 2, B11 not equal to B22. The degeneracy has been lifted in this case by B. There was a twofold degeneracy. Those eigenvectors continue to be eigenvectors of B. They are eigenvectors of A corresponding to a twofold degenerate eigenvalue. They continue to be eigenvectors of B, but the degeneracy has been lifted. So this is one case that we have. Let us look at the last case, which is this, where B11 equals B22, but modulus of B12 is not equal to 0. So let us look at that case now. What is it that we get? B11 equals B22 and modulus of B12 not equal to 0. So what is it that we have here? The root beta 1 would be B11 plus B22 by 2 plus, now this object, this whole exponent was simply plus square root of B11 minus B22 the whole squared for modulus of B12 the whole squared. This was beta to begin with. This exercise simply tells us that beta 1 in this case is B11 plus B22 by 2. This quantity vanishes plus twice modulus of B12 by 2, and therefore I have B11 plus B22 by 2 plus mod B12. In the other case, beta 2 would correspondingly be B11 plus B22 by 2 minus modulus of B12. Once more, I have two distinctly different eigenvalues, and since B11 equals B22, we have beta 1 equals B11 plus modulus of B12 and beta 2 equals B11 minus modulus of B12. You can now see that you could repeat this argument and you will get conditions on C1 and C2. In other words, if you started by saying is beta 1 C1 psi 1 plus C2 psi 2, what is it that I have? I have, if I work with the inner product of psi 1 with this object, if I did this, the first term is C1 B11 plus C2 B12 is equal to beta 1 C1. The second term there drops out because psi 1 is orthogonal to psi 2. B11 is not 0, B12 is not 0. Therefore, I have C1 B11 minus beta 1 is equal to plus C2 B12 is equal to 0. Neither B11 or B12 are 0. This would therefore lay conditions on C1 and C2. Similarly, if I started with beta 2 here, it would lay a different set of conditions on C1 and C2. In other words, this is the situation where degeneracy is lifted by B, that is beta 1 is not equal to beta 2, but all superpositions of the form C1 psi 1 plus C2 psi 2 are not eigenstates of B. Specific superpositions are the degeneracy is lifted. Once more, we have found a complete set of common eigenstates of A and B in this case, and B lifts the degeneracy. There was a two-fold degeneracy which was lifted in this case as well. Whatever I have said for a two-fold degeneracy can be extended to a G-fold degeneracy. So, the problem has the following outcome, that if you have two Hermitian operators that commute, you can find a complete set of common eigenstates of these two Hermitian operators.